Hello, dear students and parents. Welcome to Maxmuller Global Education. This is C.H. Srinivasrao. I am teaching chemistry for the last few years. Now, this year onwards, Maxmuller Education is providing online education solutions. So, hope all of you follow these online classes. Now, based on the content given in the study material provided by the Maxmuller Education, now I am going to explain a topic from 10th class, that is classification of elements into SPDF blocks. You all know that in the modern periodic table, all the elements are classified into 4 blocks. They are SPDF blocks. How these elements are classified into SPDF blocks? The elements in the periodic table are classified into SPDF blocks based on the differentiating electron. Now, what is meant by differentiating electron? Differentiating electron is nothing but the last entering electron into the orbitals of an atom is called differentiating electron. Based on this differentiating electron, all the elements of the periodic table are classified into these SPDF blocks. Before going to this type of classification, now let me introduce, we should have some idea about the structure of the atom. All of you know that the central part of an atom is called nucleus. Let this is nucleus. The space, that means around the nucleus, the space around the nucleus, which is called extranuclear region, all the electrons are revolving around this nucleus in circular orbits. These circular orbits are denoted by K, L, M, N, O, so on. These may be numbered as 1, 2, 3, 4, 5, so on. There will be infinite number of orbits for any atom. Now, for an atom, the last shell which is filled with electrons is called valence shell. The last shell which is filled with electrons is called valence shell. So, valence shell is generally denoted with small l. This is valence shell. The last but one shell is called penultimate shell, which is denoted as n-1 shell. This is penultimate shell. And the shell, third shell from the last, is called anti-penultimate shell, and it is denoted as n-2 shell. This is the anti-penultimate shell. Right? Now, we all know about this structure of atom. It is the fundamental thing. Now, how elements are classified into SPDF blocks? If the differentiating electron enters into NS sublevel, that means S sublevel in the valence shell, then it is called S block element. If the differentiating electron enters into NP sublevel, that means P sublevel in the valence shell, it is designated as P block element. And if the differentiating electron enters into n-1 d sublevel, that means d sublevel of the penultimate shell, it is called d block element. And finally, if the differentiating electron enters into n-2 f sublevel, that means f sublevel in the anti-penultimate shell, it is called f black element, right? So this is the way how SPDF black elements are classified. Now, where these SPDF black elements are arranged in the periodic table? You all know the outline of the periodic table. The outline of the periodic table is just like this. How SPDF blacks or elements are arranged in the periodic table. You all know that. Completely at the extreme left of the periodic table, S black elements are placed, and at completely right of the periodic table, P block elements are placed and D block elements are placed in between the S and P block elements. So here D block elements are placed. Now F black elements are arranged at the bottom of the periodic table to maintain the symmetry of the periodic table. So this is 4F series lanthanides and this is 5F series. So this T series consists F black. All the elements of F black are placed here. This is the placement of SPDF black elements in the periodic table. Now, we will discuss briefly the properties of SPDF black elements in detail one by one. Now, first S black elements. Now, we are going to discuss all these different types of elements in detail one by one. First, S black elements. So in these S black elements, as already I said to you, the differentiating electron goes to, the differentiating electron enters NS sublevel. That means S sublevel present in the outermost shell. Now, you all know that S sublevel can accommodate a maximum of 2 electrons only. That's why S black consists of only 2 groups. They are first A group called alkali metals and second A group called alkaline earth metals. So, S black consists only 2 groups, first A, second A. First A group elements are called alkali metals. Second A group elements are called alkaline earth metals. You all know the alkali metals. They are lithium, sodium, potassium, rubidium, cesium, francium. And alkaline earth metals are beryllium, magnesium, calcium, strontium, barium and radium. Now, the general valential configuration for S black elements is, that is, general valential configuration for S black elements is NS122. For alkali metals, the electronic configuration, general valential electronic configuration is NS1. That means they are having 1 valence electron in their outermost shells. For alkaline earth metals, for 2A group, So the general outermost shell electronic configuration is ns2. That means they are having 2 electrons in their outermost shell. Now, S black elements are highly electropositive. That means they have a tendency of losing electrons to get the nearest inert gas configuration. If alkali metals loses 1 electron, they will get the nearest inert gas configuration. That's why alkali metals form M+1 ions. That means they form univalent cations. Alkaline earth metals, if they lose 2 electrons, they will get the nearest inert gas configuration. That's why they generally form M+2 ions. That means divalent cations. So they form cations readily. That's why S black elements forms ionic compounds. They form ionic compounds. Now, coming to their nature, except hydrogen, all the S black elements are metals. Except hydrogen, which is a non-metal, all the remaining S black elements are metals. Next, since they have a tendency to lose electrons to form cations, these elements are strong reducing agents. So these are strong reducing agents. And finally, these S black elements exhibit fixed valency. That means alkali metals exhibit +1 oxidation state. They form only monovalent cations. Alkaline earth metals form divalent cations only. They have fixed valencies, fixed oxidation states. So this is all about S black elements. Now we are going to discuss P block elements. Now, let us discuss P block elements. The elements in which the differentiating electron enters NP sublevel are called P block elements. NP sublevel means P sublevel of the outermost shell. So, in these elements, the differentiating electron enters NP sublevel. You all know that P sublevel can accommodate a maximum of 6 electrons only. That's why P block consists of 6 grooves. All the P block elements are arranged in 6 grooves. They are from 3rd A to 7th A grooves, including 0 group also. So P block consists of 6 grooves. They are from 3rd A to 7th A and 0 group also. Now, what is the general valential configuration of P block elements? The general valential configuration is NS2 NP126. So This is the general valential electronic configuration. Now, what is the nature of p block elements? In p block, all types of elements are there. Most of the non-metals, metalloids, all metalloids, and few metals are also included in p block. So p block contains non-metals, most of these elements are non-metals, metalloids, that means semi-metals, and few metals also present. So metals. Now, what type of compounds are formed by p block elements? P block elements form both covalent compounds as well as ionic compounds, especially halogen family elements, oxygen, sulfur. So these can form covalent as well as ionic compounds. So p block elements form ionic as well as covalent compounds. Now, what about their valency? S block elements are having fixed valencies, whereas p block elements exhibit variable valency. That means same element may exhibit different types of valencies. I will give one or two examples for that. So these exhibit variable valency. If you take lead, which is the p block element, it exhibits +2 valency, +2 oxidation state as well as +4 oxidation state also, like that. Tin exhibit +2, +4. Bismuth exhibit +3 valency, +3 oxidation state and +5 oxidation state. So this is all about the p block elements. Now we are going to discuss d block elements. Coming to d block elements, in these elements the differentiating electron enters n-1d sublevel. That means d sublevel present in the penultimate shell of the atom. So in these elements the differentiating electron enters n-1d sublevel. Now, a d sublevel can accommodate a maximum of 10 electrons. That's why d block consists of 10 groups. That is from third B group to second B group. So totally 10 groups are present in this d block. So d block consists of 10 groups and 4 series. So these are arranged in third B, fourth B, fifth B, sixth B, seventh B, eighth group. Actually, eighth group consists of 3 subgroups. Transition triads are present in eighth group. Next, first B group and second B group. So d block starts with third B group, ends with second B group. Right. Now, what is the general electronic configuration of d block elements? General electronic configuration is ns122 n-1d 1 to 10. Now, these elements are also called as transition elements. But there is small difference between D block elements and transition elements. What is the difference? Except second B group, which consists of zinc, cadmium, mercury, all the remaining D block elements are called as transition elements. Why the name transition elements? This is because if you move in the periodic table from left to right through D block elements, there is a transition in the properties from highly electropositive to highly electronegative elements. That's why these elements are called as transition elements. Now, all these elements are metals. Now, D block elements exhibit certain characteristic properties. What are the characteristic properties? So, these D block elements exhibit certain characteristic properties. These elements exhibit variable valency. That means, same element may exhibit different oxidation states. If you take copper, it exhibits two valencies, cuprous, that means Cu plus 1, cupric, that means Cu plus 2 ion. Like that, iron exhibits Fe plus 2 ferrous and Fe plus 3 ion, which is called ferric. So these exhibit variable valencies. These form colored ions mostly, and these exhibit paramagnetic nature. And these elements forms alloys. You all know that alloy means it is a homogeneous mixture of two or more elements, which may include metalloids and non-metals also. If you take brass, it is an alloy of copper and zinc. If you take bronze, it is an alloy of copper and tin. So, D block elements also form complex compounds. They form interstitial compounds. So, all these are the characteristic properties of D block elements. Now, we are going to discuss F block elements. Now, coming to F block elements. In these elements, again, the differentiating electron goes into n-2 F sublevel. That means F sublevel present in the anti-penultimate shell. So, here differentiating electron enters n-2 F sublevel. All the F block elements are present in the same group, that is third B group. So, F block elements belong to third B group. Third B group. Their general electronic configuration is NS2. That means two electrons are present in the NS sublevel. N-1D 0 to 1. 1 or 0 electrons may be present in the D sublevel of the penultimate shell. N-2 F 1 to 14. That means F sublevel in the anti-penultimate shell may have 1 to 14 electrons. So these elements are arranged at the bottom of the periodic table to maintain the symmetry of the periodic table. These elements are actually arranged in two series. One is 4F series and second one is 5F series. 4F series elements are from cerium 58 to lutetium 71. 5F series elements are from thorium 90 to lawrencium 103. 4F series elements are also called as lanthanides because they have similarity with lanthanum closely in their properties. 5F series elements are called as actinides because of their similarity with actinium, so they are called as actinides. These elements are also called inner transition elements. Inner transition elements. All the actinides are radioactive elements. So that means they are unstable. They have a tendency of spontaneous decay into other elements. So actinides are radioactive elements. Now, what is the common oxidation state exhibited by these elements? What is the common valency exhibited by these elements? That is +3. The common oxidation state is +3. So, almost all these elements exhibit commonly +3 oxidation state. So, these are the properties of black elements.